When you have equations with just x and y, they can be represented geometrically by lines. However, when you have equations in x, y, and z, which are sometimes called coordinate triples, you can have these represented by planes rather than lines, and ideally the three planes will intersect in one nice, neat x, y, z solution. Now, when you go to graph these, you can't just say here's my x-axis and here's my y-axis. You need a z-axis that sticks straight up out of the paper. And so what we usually do is we draw this diagonally with a little dotted line in the background telling us it's going into the background here. And it's very hard to represent a three-dimensional image on a two-dimensional piece of paper, but we do the best that we can. Ideally here, we are going to want to get a solution set where we have a nice, neat XYZ solution. However, as you can see illustrated here, there are more than just one way for three planes to intersect. In this first case, there's actually no solution at all because the system is inconsistent. There is no solution set. There is no point XYZ that is common to all three planes. Same thing here, when you have parallel planes, there is no point in all three planes. And in the third place, even though two planes are the same, the third plane is different and you've got parallel planes, you have no solution in this case. In this bottom section here, you have situations where you have infinitely many solutions. This kind of looks like the binding of a book with different pages sticking out here. Any point that's on that line is a point that is common to all three planes. We will not be dealing with this type of solution set in this course, but we will in our college algebra course. So I wanted to call that to your attention. Here, where all three planes are the same plane coinciding with each other, then there's going to be an infinite number of solutions also lying on the plane. We, however, are going to be focusing on this first type of solution set for the problems that we work on. Okay, notice we have three equations and three unknowns, and the whole goal here is to get a solution out of this. We do not have any missing coefficients, and I'm actually starting on a more challenging problem. We'll go back to some easier ones, but I want to show you the whole process. I'm going to look at the coefficients of x, y, and z separately and try to find a variable to eliminate. And I notice that the coefficients of y are going to work easily for us because 3, 2, and 1 all go into 6, whereas if I eliminated x or y, I'd have to deal with the least common multiple of either 20. So let's create 6 y's in each of these positions. I'm going to work with the first two equations only to eliminate the y's, and I will create 6 y's, multiplying the first equation through by 2 and the second equation through by 3. It is very helpful to organize your work when you're doing this type of problem. This first equation is going to become 2x minus 6y minus 8z is equal to negative 14, and the second equation multiplied through by 3 will be 15x plus 6y plus 6z is equal to negative 3. Notice how we designed it specifically to eliminate those y's, and adding down we have 17x minus 2z is equal to negative 17. And I put that in red on purpose. Now I need to get the third equation involved, and I like to usually, just for organizational purposes, use the second and third equation. This time I don't need a least common multiple of 6, but 2 will do. So I'm going to leave the middle equation as is and multiply that bottom equation by 2. That middle equation will slide over. 5x plus 2y plus 2z equals negative 1. And the bottom equation, multiplying through by 2, gives me 8x minus 2y minus 10z is equal to negative 12. Adding down this time, we are going to get 13x, canceling out those y's, minus 8z is equal to negative 13. Now let's look at what we have. We've got two equations here in red, both of which only have x and z in them. So I'm going to focus on them as our system and eliminate the z's. Notice they both can go into 8z, and I'd like one to be positive and the other to be negative, so I'm going to multiply that top one by negative 4. When I do that, my top equation becomes negative 68z plus, x plus 8z is equal to 68, and the bottom equation just sliding over is 13x minus 8z equals negative 13. And again, we designed this specifically so that the z's would cancel each other out, and we have negative 55x is equal to 55. And we can divide each side by negative 55 to get negative 1 as a value of x. Okay, we have part of our solution set. Now let's take that value of x and substitute it into one of these equations to get a value of z. We choose one of these equations that has two variables in it, and for ease I'm choosing this bottom one because it's easy to draw my arrows. Substituting negative 1 in for x gives me negative 13 minus 8z is equal to negative 13, and adding 13 to each side gives me 8z is equal to 0, and therefore z is equal to 0, and I have another part of my solution set. I need, however, to find out what y is. So I'm going to go back to the bottom equation there because it only has a coefficient of negative 1, and I'm going to rewrite that equation there. It is 4x minus y minus 5z equals negative 6. And let's substitute in the values we've found. We've found that x is equal to negative 1 over here on the right. So substituting in negative 1 for x and 0 for z, we will have negative 4 minus y minus 0 is equal to negative 6. Adding 4 to both sides, we have negative y is equal to negative 2, and therefore y is equal to 2. Now, my solution set is kind of spread all over the place, but technically we are looking for the coordinate triple in xyz form, which is negative 1, 2, 0, as our solution set, and that is checkable by substituting it into all three of the original equations and verifying that yes, indeed, it does satisfy the problem.